Hi, in this video today we're going to be looking at inverse normal problems. If you looked at the previous videos, you'll see that the last video we were dealing with normal distribution problems where we were given a x value, we had to find a probability, and these questions we're going to do the reverse. We're going to be given a probability and asked to find the x value. So first thing to understand that's important is this little table at the bottom of the normal distribution table on your formula sheet. What this table shows you is for different probabilities what z values correspond to those probabilities. So once again, like the tables, we're talking about a probability from a z value all the way down. So if you looked up 1.645 in the table, you'd get 0.95. What we're going to be doing in this video is, given the probability 0.99, what's the z value? So use the table if you can. So here's some examples of how we'd use the table to do these inverse normal problems. The first question asks, what's the value of a so that the probability of z being less than a is 0.8. So here we're given the probability, given this area is 0.8, and I want to know what the value of a is. First thing that you should know is that a is positive. Remember that this distribution is symmetrical, so from the middle there all the way down, from 0 all the way down is going to be 0.5, so a is going to be a positive value. Okay, so what we're looking for is 0.8 in the body of the table and then to read off the z value from there. If you look around closer, you'll see that there's no 0.8 exactly. So what we have to do is find the closest value to 0.8 that is below 0.8. Alright, so if we go to 0.8023, that's too many. 0.7995 is the closest one below 0.8. What we need to add on to that to get to 0.8 is 5. So we look across at our last decimal place that we're going to use and find the 5 in that row, or the closest number to it. In this case, we've got it spot on. So the z value that we read off is 0.842, and that's the answer we're looking for. Second example, we want the value of b, so the probability z is greater than or equal to b is 0.072. So a diagram really helps here. 0.072 is that area there. Remember, the table only deals with z values and down, so the actual value we're going to be looking up in the table is 0.928, 1 minus 0.072. So I'm looking at 0.928 in the table. I get as close as I can, which is 0.9279. I need an extra 1. There it is there. So the z value I read off is 1.461. And that's the answer to the question. Third question, this one we want the probability of z being less than or equal to c being 0.356. Now c is on the left of 0. Because this probability is less than 0.5, I know that this c value straight away is going to be negative. Remember, the tables don't have negative values, so what we have to do is convert this problem to one where the z values are positive. So I've called this little value here c dash, and I'm going to find this value so that that value and above is 0.356 in the table. Alright. If that's going to be 0.356, the value from there and down is 1 minus that, or 0.644. Now that's the value I'm going to be looking for in the table. Remember that this value we're going to look up is going to be positive, but because of the symmetry of the normal distribution, the value that we want to find will just be negative, whatever this one here is. Okay, so we look for 0.644 in the table. This is too big, 0.6443, we're over. 0.6406 is the closest one underneath there, and we need another 34 onto there to make up to 0.644. There it is right there. So we read off our z value, 0.369 is the z value we're looking for c dash. So the answer for c is negative 0.369. The probability z is greater than d is 0.945. So we look at the table here. Look at the diagram. From there and above is 0.945. Once again, you can tell straight away this is going to be negative. So what I'm going to do is find the value of d dash. So there and below is 0.945. So I'm going to be looking at 0.945 in the table, getting this value, and then just making it negative. Okay, so the closest value underneath 0.945 is 0.9441. If you go down to the next row, you see it's too big. So we want 0.945, so we want another 9 added on to that. 0.9441 plus 0.0009. you can see there's no value in the table that gives us exactly 0.945, so we just choose the closest. So we could have gone with 8 or 10, either one of these. So I've chosen 8, which gives us a z-value of 1.597. That's d dash, so the value for d is negative 1.597. Part E asks us to find the probability of z being between two values that are the same, and that probability is 0.95. So we've got some symmetry going on here. Once again, draw a diagram, it makes life really easy. Here's 0.95, or 95% of the area is contained between this value and this value here, which leaves us 2.5% at each end here. So if I look up this value here, so that there and above is 2.5%, it means from there and all the way down will be 97.5%, or 0.975. Okay, so just ignore this one down here. From there and down, if there and above is 0.025, there and down will be 0.975. So that's the value that I'm looking for in the table. Now don't forget the little table at the bottom of the normal distribution tables. Here it is here. If you're looking for one of these values here, you can read it off straight away. So here's an example, 0.975 is given, and the value is 1.96. So the value of E we're looking for is 1.96. This last example uses this skill we've just learnt in context. So we've got a waiting time to order food of 3.5 minutes on average and a standard deviation of 0.8 minutes. 5% of the customers will wait less than a certain amount of time. What's that time? So this is a classic inverse normal problem. I'm giving you the probability, asking you to find the actual value. Draw a diagram, it's really important. So 5% of the customers will wait less than t minutes. So clearly t is down here on the low side. 5% of customers wait less than that amount of time. So they're being served really quickly. Remember the average is 3.5. And I want to find what that value of t is. So it looks like it's going to be just over 2 minutes. Now if we convert this problem to a problem with z-values over here, you can see that our z-value that we need here is negative. That's important that you recognize that. Our final z-value is negative. Don't have negative values in the table, so I'm going to convert it to a problem with positive z-values and try and find the value of b. So the value of b, if above b and above is 0.05, that means the probability from b and all the way down will be 0.95. So 0.95 is what I'm looking for in the table. If you look at that little table at the bottom, it gives you that value. 0.995 is one of the ones that are given, and the value is 1.645. So that's 1.645. This value of A that we're looking for is negative 1.645. So our last step here is to use this formula here that we saw before. Now we've got everything in this formula. We've got the z-value, negative 1.645. We know the mean, we know the standard deviation. What we're trying to find is the actual real life value, which I've called t in this case. So putting all the values in the formula, times by 0.8 and add 3.5 gives me 2.184 minutes, or 2 minutes 10 seconds to the nearest second. Okay, this last problem, we're asked to find the time that it takes 99% of the people to be served in. So only 1% of the people get served in a longer time than this. So this is above the mean, this one. So it's important here that you try and work out, is it below the mean or above the mean, and draw a diagram. So we're talking about slow service in this case. So you've got the actual diagram here for the t we're trying to find. 1% above t, 99% below. And here's my diagram for z-values. I'm trying to find the z-value so that there and above is 1% or there and below is 99%. This is one of the values given in the table, 0.99. If you look in the table, it tells you the z-value is 2.326. That's the z-value we want. It's the value of A. So substituting in the formula, 2.326 is x, which I'll call t here, minus the mean over the standard deviation. So we times by 0.8 and add 3.5 gives us 5.36 minutes, or 5 minutes 20 seconds. Just be aware in problems like this, if you have things like athletics and we want the best 10% of times, let's say for the 100 meters, then we'd be looking at below the mean because we want the fastest 10%. If we wanted the best 10% of javelin throws, we'd be looking for the values above the mean. Okay, throwing the javelin further is what we're looking for there. So you just have to think about it sometimes, whether you're above and below the mean.